Welcome. We're going to talk about vectors. So vector is, it has a direction and it has a length. It's a directed line segment. And so we have an initial point, sometimes called the tail, and a terminal point, sometimes called the head. A couple different ways of indicating that you're talking about a vector: bold print, a little arrow over it, or sometimes a hat. Vectors are considered equivalent if they have the same length and the same direction. Okay, and then the length, that's what we call the magnitude, and mostly that's represented, it looks like absolute value. That's how our book talks about it. Usually that's written with 2 upward bars around the name of the vector. So that's the magnitude. And if the magnitude is 1, then that's called the unit vector. Okay, and then we can put these in the coordinate plane and just find their direction and their length with, let's say that we have 2 points, x1, x2, or x1, y1, and then we have another point, x2, y2. So if I want to know the length, all I have to do is use Pythagorean theorem. Okay, so that's where this formula comes from for its length. And then in terms of, well, where is it? You know, what's the x component of my vector? What's the y component? Well, you just find the difference between your x's. And if you want to know the y component, you just find the difference between your y's. Okay, so the way that we indicate a vector is here. That's the algebraic way of showing it, where you have the x component, like how far over you went to get to the end, and then how far up you went. So this would be the a, this is the b, where a is the difference between my x's and b is the difference between my y's. And that should remind you a little bit of slope, right? Because we're figuring out how far do I have to travel over and up to get to the end of my vector. Okay. All right, I'm given 2 points. I'm given P is at 1, 3 and Q is at 2, 8. So I'm going to go ahead and draw those. Okay, and now the vector that goes between those two that starts at Q and ends at P, it has a length and it has a direction. Okay, and we're being asked to find its magnitude, so that means find its length. Okay, and just use our Pythagorean theorem there. So the length of QP is, just based on our Pythagorean theorem, we have the difference in our x's, 1 minus -2, and I could just have counted that out as well. That's 3. Okay, and then the height, right, that would be the difference between the y values, so 3 minus 8 quantity squared. And that's just 5. Okay, so then we would have that we have the square root of 9 plus 25. Okay, so our magnitude, our length, is the square root of 37. All right, so let's do some operations, some arithmetic with our vectors. We can add vectors together, we can subtract them, we can multiply them by a number, by a coefficient or a scalar number, a real number. Okay, so let me show you how this works. So let's see, if I have a vector 2, -5, 2 is the x, -5 is the y, and I'm adding 3 times the vector v, which is at the point 3, 8. Okay, what you can do is you basically just multiply both the x and the y component of your vector by 3. Okay, so we would have 9 and 24. And then what you're going to do is add the x components, 2 plus 9, so just add these guys right up. And then we're going to do the same thing with our y components, just adding our y's. Okay, so we get a final vector of 11 and 19. And it's the same idea with subtraction I'm going to think of this as 4 times, oh, I forgot what my vectors are. Okay, 4 times v, which is 3, 8. Okay, but instead of minus, I'm going to just think of that as plus negative 5 times the vector u, which was at 2, negative 5. Okay, so I'm going to distribute and then add my components. So I've got 12 and 32, and I'm adding negative 10, 25. Okay, and then we just add our x component, so 12 plus a negative 10, and then add our y components, 25 plus 32. And so our new vector is at negative 2, or positive 2, yep, positive 2 and 57. All right, so just showing you graphically what this looks like geometrically. So if we have some vectors, I'm taking the vector u and I'm adding the vector v. So when you're adding, you go from the original initial point and then you go to the final terminal point, and that's your resultant. And when you add them, what you can kind of see that you've got this little parallelogram. You can show that sort of visually. And let's see, multiplying by 2, that just takes and basically doubles our vector. Our vector went over 1, 2, 3, up 2. So we just do 2 of those, and that would be 2v. And then multiplying by negative, it just takes our original vector that went over 3 up 2, and it goes now from an initial point, it goes opposite. So it goes down and back. All right, and when we're subtracting, what we're really doing is we're taking A and adding the opposite of B. So if B went back and up, the opposite of B would go down and to the right. So then we would add the opposite of B, and that's how graphically subtraction looks. Now, it's often useful to talk about vectors in terms of what's called I and j, and those are really special vectors. They're along the x and the y coordinates, and their magnitude is 1, so they are unit vectors. Any vector whose magnitude, whose length is 1, is by definition what's called a unit vector. Okay, so these ones are just nice because we can write any vector in terms of these little unit vectors. So let me just show you. If we took negative 3 times I, and I is the vector 1, 0, and then we multiplied 10 times j, and j is the vector 0, 1. Okay, so what we would get is the vector negative 3, 0, and then we're adding 0, 10 when we apply that multiplication to our vectors. Okay, and then we would just add our x components together, add our y components together, and we have a resulting vector, which is at negative 3, 10. So you can do the same thing. So any vector can be rewritten in terms of I and j, and it's just useful for certain problems to be able to write that out in that way. All right, I'm going to do example first, and then I'll come back to this, these definitions, or just kind of that explanation. But let me just show you first. So I have this situation where I have a vector, and its length is 4, and its angle is pi over 3. Okay. Now let's say that I wanted to think about that in terms of its horizontal component and its vertical component. Using trig, we know that the opposite of an angle, the opposite over hypotenuse is sine, so it would be y over 4. And then we could solve that, multiply both sides by 4, and it would give us that y is equal to 4 sine of pi over 3. And we could actually figure that out. That would be, let's see, sine of pi over 3 is square root of 3 over 2, and then we're multiplying that by 4. So our vertical component is 2 square root of 3. And then we can do the same thing looking at tangent, or at cosine. So cosine of pi over 3, that is the adjacent, so that'd be x over the hypotenuse. And then we can solve for x. That would give us 4 cosine of pi over 3. And that is, let's see, cosine of pi over 3, that's just a half. And so we would have x is 2. All right, and then putting that together, so I could name my vector, I could either write it as 2 and then 2 root 3, right, our x and our y component. That's one way to write it, or we can write it as 2 in the horizontal direction plus 2 root 3 in the vertical direction. Okay, so that is in terms of I and j. And then this one is the algebraic one. So most of us in math prefer, this is called the algebraic form, but I just need to show you this one because that's what usually shows up in physics classes. So it's nice to be able to know what that means. Okay, and then here, this is just showing you for any angle, this idea of setting up a triangle, finding cosine, that is your horizontal, sine, that's your vertical. So just like we did in this particular example, it works for any of them. And so we can find the form, the trig form of our vector in terms of cosine and sine. Right, this is the length. This was sine of the angle. This was the length, so there's our magnitude, and then this is cosine of the angle. Okay, in this example, we're being asked to find the direction of this vector. Being a math person, I always like the algebraic form. The x component is 1, and the the vertical component is negative root 3. Okay, so we can go ahead and draw a diagram. Okay, so in my quadrant, I'm in quadrant 4, and I have an x component of 1 and a y component of negative 3. Okay, so to find the angle of my vector, well, let's see, the reference angle would be, let's see, tangent of the reference angle would be opposite, so negative square root of 3 over 1, and then just find the arctan. Right, or if you just have that memorized, that is at pi over 3. So that's the reference angle. And now, because we're in quadrant 3, we need to know the angle of our vector here would be at 5 pi over 3 or 300 degrees. Okay, we can try another one. I'll go ahead and draw this one out. Okay, and then I can find the reference angle here by taking, because we know if we took tangent of our reference angle, that would be opposite, which is 7 over adjacent, which is negative 4. And then I'm just going to find the arctan, and I'm going to be in degree mode. So then that gives us the reference angle is about, let's see, what is that, about negative 60.26, just because arctan is only defined within quadrants 1 and 4. Okay, so what's gonna come out on your calculator is actually gonna be this angle, negative 60.26 degrees. Okay, all right, but what we actually want is not either of those. What we want is that the angle of the vector. We want this angle right over here. Okay, so if you take 180 plus your negative 60.26, that's going to give you the angle that you want. So your angle is approximately 119.74 degrees.